Okay, hello everyone. Welcome to Altibase webcast presentation. First of all, is anyone first time to listening to the session? Okay, just in case you don't know me, my name is Daniel Seo. I'm an education consultant in Altibase Corporation. Okay, today we're gonna talk about how to manage buffer in Altibase HDB. Okay, did you ever know that Altibase also use the buffer? Okay, because Altibase um, is hybrid database, which means in memory, there's an area for saving memory data and disk data separately. Okay, the space for managing memory data is where data for memory table space is saved, and the space for managing disk data is called buffer. This area is where data for disk table space is saved and managed. Here's what we're gonna have a look at today is the concept, contents, and the management of the buffer. Okay, let's take a look at what those are. Okay, for those of you who are familiar with the disk table space, will also be familiar with the buffer. Okay. For disk database, when transaction is executed, it has to access particular data from the data file because all of data is stored in a disk. However, if it keeps accessing data from the disk, it will have numerous amount of disk I/O, so that the performance of transaction will be remarkably reduced. Okay, so to solve this issue, many of disk database put some of this data into memory area, and this memory area is called buffer or the buffer pool. And because not all of this data is cached into the buffer, some data might not be in the buffer when the user requests for particular data. Okay, then is the transaction gonna be fail when there's no data from the buffer? Okay, not at all, because when it is not in the buffer, that doesn't mean that it's not in the disk as well. Okay, so let's say there's a data in the disk but not in the buffer. So the requested data is in the disk and the data needs to be accessed, but how? So it firstly puts data into memory buffer, not like accessing from the disk straight away. However, when database is online, the buffer pool is full most of the time. Okay, mostly the database does not operate with empty buffer. Therefore, in order to cache new data from the disk to the buffer, the original data from the buffer has to be deleted, and the new data has to be uploaded instead. The smallest unit of saving data is called a page. Okay, so it is processed by page unit, and we call this process as buffer replace. Okay, meaning the original page that was previously cached to the buffer is new disk page. So when buffer replace is executed, the buffer actually deletes the required number of page and copies the new page from the disk and cache into it. Here, the page that is deleted from the buffer is called victim. Okay, it's called victim. When you look at the diagram, the red part represents the buffer, and the blue part represents the disk pages. Okay, so for example, there are 10 disk pages, and 4 of them are cached into the buffer. And user requests the page number 1, which is not in the buffer. Then the disk has to unload the page number 1 from the disk to the buffer. Okay, but the buffer is full, so it has to delete one page from the buffer. Okay, here the page that is deleted is called victim. Okay, the page number 1 from the disk is unloaded to the buffer and then it is returned to the user. This process is called buffer replace. Okay, so far I explained about the brief concept about the buffer, and now I'm going to talk about the contents and the management types of the buffer. Okay, now let's have a look at some contents about the buffer. This thing says buffer pool. This one is the same as buffer. The term pool means a collection of something. So let's have a look at what the pool comprises of. Okay, the pool is buffer pool is where the buffer frames are gathered together. So like I said previously, the buffer is where this page is copied into. So the buffer frame is where this page is copied and saved. Okay, so the buffer pool comprises of buffer frames. So the buffer frame is where the page is cached into. Okay, then what is BCB then? Okay, this BCB is the object that manages buffer frame. So when user requests data, the BCB manages information about buffer frame to help to efficiently access to page in a buffer frame. Okay, and the list is the something where similar kinds of BCBs are gathered together. Okay, but they are not just single BCB. There are lots of them, and their types are different depending on the information of the buffer frame that is managed by. Okay, so this is why it has to be managed by the list, because when same types of BCBs are gathered and managed in a list, then the cost of managing buffer can be saved and minimized. Now let's have a look at each of the contents. Okay, so buffer frame is where this page is loaded, and BCB manages buffer frames information. The list manages BCBs. Okay, so like I said previously, about the buffer frame, it means where this page is copied into. So you can think it as space where real data is saved into, but Altibase use the page for smallest unit of saving this data, which is 8 kilobytes. Okay, so when a page is copied into the buffer frames, it means the size of buffer frame also becomes 8 kilobytes. If the size of page is 8 kilobytes. Okay, then for example, when we assign the size of buffer pool for 100 megabytes, then you'll be able to calculate how many buffer frames are created inside. So the number of these pages is depending on the number of buffer frames. And because the page where actual data is saved is cached into the buffer frame is managed in 3 different ways. Okay, so there are the 3 different ways. The free, clean, and dirty. Okay, the free means the buffer frame is empty. Okay, this isn't usual. Database is online except when database is starting up, or when database is dropped. Okay, it starts from free status, and once the page from the disk is copied into buffer frame, then the status buffer frame becomes clean. Okay, the clean status is where the page is copied into buffer frame, but the data is not modified, which means the contents of the page in the buffer frame and the page on the disk are the same. When the user executes the select and it is copied into the buffer frame, however, there's no modification of data, therefore the status becomes clean. Okay, when there's a modification of data while in clean status, then the status of buffer frame is also changed, and we call this state dirty. Okay, and because the data is modified, therefore the buffer frame that has dirty status is different to the page in a disk. Okay, lastly, the term flush means is reflecting the contents of the page in the buffer to the disk. In order to reflect the contents of the page, the contents of the buffer frame and the contents of the disk page have to be different each other. Okay, so only the page that has dirty status is flush. So once it is flush, the contents of the buffer frame and the contents of this page become same. Therefore, the status of the buffer frame changes from dirty to clean. Okay, so the status buffer frame is changed by modifying operation, flush, and etc. Also, whether it can be replaced or not is depending on the status of the buffer frame. Okay, so like I said previously, there's an object that manages information and the status of the buffer frame, and that is BCB. Okay, the BCB stands for buffer control block, and it manages buffer frame one to one. Okay, for example, if there are 100 buffer frames, then there are also 100 BCBs as well. Then what information does BCB manage? The following information is managed. Okay, they are not just single BCB, but it's depending on the number of buffer frames. So each BCB gets ID. Okay, it gets ID. And when user requests for data, it firstly accesses BCB first. The BCB does not contain actual data. The actual data is cached into the buffer frame, which is managed by BCB. So BCB manages the memory address. The memory address of the buffer frame, which is managed by BCB. Okay, so when we look up the address value managed by BCB, we can find out the buffer frame where the data that the user requested is saved into. And what it also manages, that it also manages table space ID and page ID. Okay, this one. For example, let's say we create this table space that has 100 megabytes. So once the table space is created, then firstly the ID is given to it, and the 100 megabyte of number of pages are given to the table spaces. It's not just a single page, but it's many of them. So the ID is given to each page. Okay. So when this page is cached into the buffer frame, the information about the ID of the page that belongs to the ID of the table space is also saved. Okay, the reason why the BCB manages this kind of information is because to minimize the cost of accessing data that the user requested. Let's say that the user wants to inquire data that meets the condition of C1 equals to 10 from the T1 table, and then the data that satisfied with C1 equals 10 comes by the information of which page number of which table space through the index. Okay. Then by using that information, the BCB that manages page which the user has just requested can be easily found. Okay. And there's no data inside BCB, therefore when address value is looked up, managed by BCB, the buffer frame where actual data is saved into can be easily found. Okay, that's the reason why the BCB also manages information about which page is saved into buffer frame. Okay, next is the status of buffer frame. The status. Okay, like I said before, the BCB manages three types of buffer frame status. The reason why status is managed is because to know which buffer frame has to be flushed and which buffer frame has to be replaced. I said when page status is dirty, because the contents of the buffer frame, the contents of this page are different, therefore it has to be flushed. So when it is dirty, it can either be victim or be replaced. So when looking for a victim, the status of buffer frame managed by BCB has to be considered. I said these BCBs are managed by gathering them together, so the BCB manages information about which BCB belongs to which list. Okay, the way of accessing BCB is different depending on which BCB belongs to which list. I'll talk about this in later slides when we talk about the list in more detail. When the number of BCBs got increased in the list and they can be managed parallel, so the list number is also managed. Okay, it is a bit complicated as there are a lot of them to be managed in BCB, but to summarize them, BCB is the object that manages various information about the buffer frame to minimize the cost of accessing data. Okay, next is the explanation of the list. Remember, the list is used to manage BCB by gathering similar types of BCBs. Then let's have a look at which lists are used and which list manages which types of BCBs. Okay, first of all, okay, the flush list is the easiest to understand. The flush list is literally means the list that collects BCB to flush them. Like I said previously, only the dirty buffer frame is flush. Okay, then let's suppose there are 10,000 buffer frames in the buffer pool. Okay, then there will be also 10,000 of BCBs. And how are we gonna find a dirty status that has to be flushed? If the only dirty ones are not gathered, then like a full scan, all of 10,000 BCBs have to be checked in order to flush dirty ones. If this happens, the cost of flush would remarkably increase. Okay, so the flush list is where only the dirty BCBs are gathered together. Okay, so when flushes occur, the buffer flusher flushes the buffer frames of BCBs that are gathered in a flush list only, without checking BCBs from other lists. So the purpose for flush list is to flush only. Okay, the next list we will have a look at is called prepare list. The word prepare means preparing something. So what it prepares is that it prepares the BCBs for replacing. Okay, I said previously the dirty buffer frames cannot be replaced, but let's say there are 10,000 buffer frames and they are mixed with clean and dirty. Okay, then again, they have to do all the full scan in order to find the victim. Okay, so to minimize the cost of replacing, the prepare list collects the BCB that can be used for victim only. Okay, if it's managed like this, the same for flush list, the buffer replace could be faster as a victim is found straight away from the prepare list when replacing occurs. Okay, the other PCBs are managed from LRU list, okay, by using LRU algorithm. The LRU algorithm is managed by sorting the buffer page in a cache order. Okay, okay, the three lists that I just talked about, uh, it moves the BCB to other lists when their main goal is accomplished. The main goal of prepare list is to secure the victim for replacing. So once it is replaced, the BCB is deleted from the prepare list and it is moved to LRU list. Same for flush list. The main goal is when flush is over, the status is changed from dirty to clean, so it is deleted and it is moved to prepare list, and it enables victim to be used for next replacement. But you should know that becoming dirty ones does not mean that they are moved to the flush list straight away. The dirty BCB can also be managed from prepare list and LRU list. But in order to move BCB to the flush list, the dirty BCB has to be found when looking for victim. So it means that the dirty page may not be flushed into the disk as a victim, is not found yet, even though the user successfully changed the data. So by using checkpoint list, it manages all the dirty BCBs of three lists to prevent the data difference between buffer and a disk. And because all of the dirty ones are additionally managed in checkpoint list, the buffer frames which are not flushed by the flush list can be flushed by the checkpoint list. So there is no such case that the data from buffer and data from disk are not synchronized. Okay, so what I just talked about so far could be difficult to understand, but once we check again by looking at the example, then it will be easier to understand. Okay, the diagram you're looking at is the method of accessing the data which the user has requested when the data is cached into the buffer. The yellow part that represents the buffer pool, and the blue part comprises of buffer frames, 4 buffer frames actually. And because there are 4 buffer frames, there are also 4 BCBs, and the sum this page is cached into each buffer frames. Okay, so the client just inquire data for C1 equals 30. Then the execution plan for the SQL sentence is made from the query processor, and this execution plan contains information about whether C1 equals 30 is saved into which page. Okay, so when accessing the buffer, that's why it firstly accesses the BCB. Okay, and because the BCB manages information about which page is cached into the buffer frame, so that's why it can easily access the BCB, which manages page ID that is already checked from execution plan. Okay, so here in diagram, we just check that BCB number 2 manages the page where C1 equals 30 is saved. Okay. Then because there's no actual data in BCB, so when we look at the address value, we can check the data C1 equals 30 is cached into the buffer frame, and you can return the data that the user requested. Okay, so when modifying data or inquiring data that is cached into the buffer, you can handle faster from the memory, so you can also do the fast transaction for this data. But when it is not cached, then it has to be replaced. That's why the performance is reduced. Okay, then let's have a look at another example for replacing and managing the list. Okay, the yellow part, they represent buffer pool like a previous diagram. The buffer pool comprises 3 buffer frames, and there are also 3 BCBs. Okay, a single BCB is managed by prepare list, and other 2 BCBs are managed by LRU list. Okay, so now let's have a look at how they are activated in a buffer when multiple transactions are executed while 3 disk pages are cached into the buffer frame. Okay, first of all, the client requests the data for C1 equals 10. Okay, like I said previously, it can access to the BCB of page straight away because they can know whether the C1 equals 10 is saved into which page by the query processor. In the diagram, we just check that BCB number 2 manages the request to page. Okay, when the address value is checked by the accessing BCB, the request data can be returned as the data C1 equals 10 is cached into the buffer frame. Okay, now the C1 equals 20 is updated to C1 equals 2. So for an update, the data needs to be changed, then it has to access to the save page first. So it looks for which PCB manages particular page where data is saved into. Okay, we can check that PCB number 3 manages particular page, and when address value is checked, the C1 equals 20 is saved into that page. Okay, so when data is modified, the buffer frames become dirty. As the contents of the buffer frame and the contents of the disk page become different. Okay, so like a diagram, being dirty doesn't mean that it is moved to flush list straight away. This PCB can only be moved to flush list while looking for victim. Okay. Okay, if there is no buffer replacement, there could be dirty PCBs left in LRU list. Okay, in a prepare list, and they are not flush even though the buffer flush occurs. So that's why they are managed by checkpoint list, so that they can be flushed when checkpoint flush occurs. Now let's check C1 equals 40 data. Now the PCB that manages page when C1 equals 40 is safe has to be found. Okay, but this page is not cached into the buffer yet. Okay, when this happens, the buffer replace has to be executed. Okay, do you remember where to look for a victim when replacing? Okay, the prepare list. The prepare list is checked, and there's one PCB, and then this PCB can be chosen as a victim and replaced. Okay, when it's replaced, the buffer frame page that PCB number 1 manages is deleted, and the page for the data that the user requested is newly cached. Okay, remember I said once the replacement is over, the PCB is deleted from the prepare list and it is moved to LRU list. Now it is managed by the LRU algorithm. The PCB is now moved to very front of the list, the very left, to manage the PCB by the replace order. Okay, so when they are in a queue like this, it means they are sorted by replace order, so they can be managed by LRU algorithm. And the page is already cached into the buffer frame, so it is returned to the user. Now, let's check the data. C1 equals to 50. The same situation, it is not cached into the buffer. Then what now? The replacement. Okay, in order to replace, the prepare list is checked, but there's no PCB. When this happens, it looks for victim from the LRU list, and because in LRU list they are sorted by the replace order, so the oldest replaced PCB is located from very right end of the buffer. Then that oldest PCB is supposed to be replaced. But for PCB number 3 is dirty state, so it cannot be replaced. So it is moved to the flush list, and again it looks for another victim from the very end. However, when the PCB number is checked, it is clean, so it can be replaced. So the buffer frame page that is managed by PCB number 2 is deleted, and the new page from the disk is cached. And because select is executed, the clean status of PCB is maintained and the data is returned to the user. Okay, another update has been executed. Now it is changing from C1 equals 40 to C1 equals 4. Now you will know how it will be processed. So first of all, okay, it accesses to the PCB that manages page where C1 equals 40 data is saved. And because it is managed by PCB number 1, it looks up the address value and changes the value to 4. The PCB status is changed to dirty as the data is modified. Okay, and it is not moved to flush list, but it is managed by adding to the checkpoint list. Okay, now let's flush into the disk. When flush happens, the buffer flusher flushes PCBs and they are in a flush list only. Okay, only the buffer frame that is managed by PCB number 3 is flush, and synchronized with the disk. And once it is flushed, the dirty PCB is deleted from the flush list and it goes to the prepare list and becomes clean status. And because the PCB number 1 that is not flushed into the disk is still being managed from the checkpoint list, it is synchronized with the disk when checkpoint flush happens. Okay, so it's pretty much about today's topic, the buffer management. Okay, I hope you guys enjoyed today's session pretty well. Okay, in next time we're gonna talk about the replication. Okay, the replication part 1, the overview. Okay, thanks for listening. I'll see you guys next time.